Swayam Prabha. Digital India. Educated India.
Welcome back to the lectures on material balance calculations for single unit systems with multiple reactions. In the last lecture, we looked at performing molecular species balance and atomic species balances for a problem which had two reactions happening in parallel. So let us try a different technique for two reactions happening in parallel today. So this example problem again has two reactions which are happening in parallel. However, the technique which we use would be different from the molecular species balances and atomic species balances which we used. The technique we are going to use is called extent of reaction technique. So let us go about reading the problem statement. In the anaerobic fermentation of grain, the yeast Saccharomyces cerevisiae digests the glucose from plants to form the products ethanol and propanoic acid by the following overall reactions. In a batch process, a tank is charged with 4000 kilograms of 12% solution of glucose in water. After fermentation, 120 kilograms of carbon dioxide is produced and 90 kilograms of unreacted glucose remains in the broth. What are the mass percents of ethanol and propanoic acid in the broth at the end of the fermentation process? You can assume that no glucose is assimilated in the bacteria. So based on the information given, we can assume steady state because there is no accumulation happening. So we will go about solving this problem. So as I mentioned, we will try to use a technique called extent of reaction technique. So we have already defined what extent of reaction is. We will try to apply that for performing these material balance calculations. To start the problem, we identify that 4000 kilograms of solution is present initially in the reactor. So the basis would be 4000 kilograms of feed. Now that we have the feed in mass, we will have to identify how much of it is glucose and what is the amount of water. We would also need to know the number of moles of glucose and water which is present so that we can use the stoichiometry effectively. So let us first identify what information we have. We have been told that 12% glucose solution is fed. This implies the amount of glucose in the feed would be 4000 times 0.12, and converting this mass to moles, we divide it by the molecular weight, which would be 180 kilograms per kilomole, giving you a value of 2.667 kilomoles. So the rest 88% is water. This implies that the amount of water present in the feed would be 4000 times 0.88 divided by 18, which is the molecular weight of water, to give the total number of moles as 195.6 kilomoles. In addition to this, we have also been told that the final product contains 90 kilograms of glucose and 120 kilograms of carbon dioxide. So we convert these masses to moles also. 120 kilograms of carbon dioxide basically would be 120 divided by 44 moles, 44 kilomoles of carbon dioxide, which is 2.727 kilomoles, and you have glucose which is 90 kilograms of glucose, forming 90 divided by 180 kilomoles, which is 0.5 kilomoles of glucose. So let us now draw the flow chart for the process. The process would look like this. We have 195.6 kilomoles of water and 2.667 kilomoles of glucose entering the system, where it gets reacted to form ethanol, propanoic acid, water, and you have 0.5 kilomoles of unreacted glucose remaining, and you also have 2.727 kilomoles of carbon dioxide which is produced. With this information, let us start solving the material balance problem. As I mentioned when we started this lecture, we are going to use a technique called the extent of reaction technique. We have already defined what an extent of reaction is. Extent of reaction for a reaction J is given as Ni out minus Ni in. So, it could either be out or final and in or initial divided by the stoichiometric coefficient of that particular reactant in the reaction J. So, this is basically a representation of the change in the number of moles of a particular component during the reaction divided by the stoichiometric coefficient of that particular reaction. So, from this equation we understand that the product of stoichiometric coefficient of a component in the reaction J times the extent of reaction J for reaction J would basically give us N out minus N in for a particular component, which is basically the change in the number of moles of a particular component. This could either be generation or consumption. Because of this, under steady state conditions, using extent of reaction, we can write the balance equation as follows. Ni out would be equal to Ni in plus sigma of J equals 1 to N nu Ij times extent of reaction for J. How did I write this equation? So, what we have is input minus output plus generation minus consumption equals accumulation, which is the general balance equation. At steady state, accumulation is 0, giving us input minus output plus generation minus consumption equals 0. So, output is basically equal to input plus generation minus consumption. This term generation minus consumption represents the change in the number of moles due to reaction. So, that can be represented as sigma of nu Ij times the extent of reaction for reaction J. And when we do this, what we have is accounting for the number of moles of each component being consumed or generated in each of the reaction which is taking place, and by finding a summation of all that, we get the total change in the number of moles for a particular component in the process. So, thereby we write this out as Ni out, in as Ni in, and that is the input, and you have the term generation minus consumption, which is represented by the summation of all the reactions times the stoichiometric coefficient of the component for that particular reaction times the extent of reaction for the particular reaction. So, using this particular equation, let us try and solve the material balance problem in front of us. For this reason, we will start with glucose, where we know the amount of glucose entering and the amount of glucose leaving, and carbon dioxide, where we know that no carbon dioxide is entering the system and we have the condition of how much carbon dioxide is present at the final condition. So, using that, let us start with glucose balance. The glucose balance would look like this. You have glucose final would be equal to glucose initial plus sigma of J equals 1 to N nu Ij stoichiometric coefficient times extent of reaction for the reaction J. Glucose actually takes part in both the reactions, which means this equation becomes N glucose final is equal to N glucose initial plus the stoichiometric coefficient of glucose in the first reaction times the extent of reaction for the first reaction plus the stoichiometric coefficient of glucose in the second reaction times the extent of reaction for the second reaction. The stoichiometric coefficient of glucose in both the reactions is 1, and we know the number of moles of glucose in the final condition and the initial condition. So, looking at the data given in the problem, we know the number of moles of glucose which is present in the initial condition and the number of moles of glucose which is present in the final condition. We also know that the stoichiometric coefficient for glucose in both the reactions is 1. However, glucose is a reactant, which means the stoichiometric coefficients would be written as -1 to account for the glucose being consumed instead of being generated. Taking that into account, the balance equation would look like 0.5 equals 2.667 minus extent of reaction for reaction 1 and extent of second reaction, giving you the summation of the extent of reactions as 2.167. So, this is one equation. Similarly, we can write a balance equation for carbon dioxide. Carbon dioxide takes part only in the first reaction. There is no carbon dioxide involved in the second reaction. For this reason, the equation becomes simpler. You have N carbon dioxide final equals N carbon dioxide initial plus stoichiometric coefficient of carbon dioxide in the first reaction times the extent of reaction for the first reaction. As there is no carbon dioxide in the initial condition, you end up with the stoichiometric coefficient of carbon dioxide times the extent of reaction for carbon dioxide in the first reaction is equal to the amount of carbon dioxide in the final condition. So, the stoichiometric coefficient of carbon dioxide is 2 and carbon dioxide is a product, which means the stoichiometric coefficient will be written as a positive 2, which is 2 times extent of reaction for 1 would be equal to 2.727, giving you the extent of reaction for the first reaction as 1.3635 kilomoles. So, substituting this back into the first equation, we can get the extent of reaction for the second reaction as 0.8035 kilomoles. Now that we have calculated the extent of reaction for reactions 1 and 2, we can calculate the number of moles in the final condition for all the reactants and products which are taking part in the reaction. For that, we should write component balances for the individual components. Let us start with the water balance. So, the water balance would be N water final is equal to N water initial plus stoichiometric coefficient of water in the second reaction times the extent of reaction for the second reaction. Water is not taking part in the first reaction and it is being produced in the second reaction. For this reason, we have used only the stoichiometric coefficient of water in the second reaction and the extent of reaction for second reaction. So, the initial amount of water is 195.6 and the stoichiometric coefficient for water is 2 times 0.8035, giving you the total amount of water in the final broth is water in broth would be 197.2 kilomoles, and we can write an ethanol balance followed by this. The ethanol balance would be again the same thing. We have ethanol final, we do not have any ethanol entering the system in the initial condition and ethanol is being produced only in the first reaction. So, this becomes stoichiometric coefficient of ethanol in the first reaction times extent of reaction for the first reaction. So, thereby ethanol in the broth is equal to 2 times the extent of reaction for the first reaction, which is 1.3635, giving you a value of 2.727 kilomoles. So, finally, we will have to perform the balances for propanoic acid. So, for propanoic acid, we do not have any propanoic acid entering using at the initial condition and we have only propanoic acid being produced by the second reaction. So, propanoic acid in the final condition would be equal to stoichiometric coefficient of propanoic acid in the second reaction times extent of reaction for the second reaction, which is 2 times 0.8035, giving you a value of 1.607 kilomoles. With this, we have the number of moles of each of the component present in the final broth. Now, we need to calculate the composition of the final broth. The problem statement requires us to calculate the composition of final broth in terms of mass percentages. So, we go back to building this table and we will write down the amounts which we have calculated. Ethanol has been calculated as 2.727 kilomoles, propanoic acid in the final broth is 1.607 kilomoles, glucose in the final broth is 0.5 kilomoles, and carbon dioxide is 2.727 kilomoles, and water is 197.2 kilomoles. The molecular weight for each of these are known and they are 46, 72, 180, 44 and 18. Using the molecular weight, we can calculate the masses as the product of molecular weight and the number of moles to get the masses as 125.44 kilograms, 115.7 kilograms, 90 kilograms, 120 kilograms and 3549.6 kilograms. The summation here would come to 4000.74. One thing you would notice is we had 4000 kilograms of feed present initially. The value we are getting here is slightly off. This is not because of mass being created, this is just because of rounding off errors. If we had not rounded off and if we had used all the decimals, we would get exactly 4000. So, the numbers which we have used are slightly off because of rounding off errors. So, using this total mass and the individual masses for the components, we can calculate the mass percentages as 3.14, 2.89, 2.25, 3 and 88.72. So, we have been asked to calculate the mass percentage of ethanol and propanoic acid in the problem, which comes out to be 3.14 and 2.89%. With this, we have come to the conclusion of this problem using extent of reaction method. As an exercise, I would want you to perform the same calculations using molecular species balances and verify if you get the same answers. With these three techniques, namely the molecular species balance, atomic species balance and the extent of reaction technique, you are now fully equipped to solve any material balance problem containing either single or multiple reactions. In the next class, we will talk about reactions which happen in series. Thank you.